edition of the Heat Treat podcast. Today we're going to talk about furnace design and engineering. And who's better to explain us about how to design and engineer a furnace than my dear friend and a great power player of the industry, Ron Waligora. How's it going, Ron?
Carlos, it's fantastic. I'm glad that you introduced me and I'm able to be a part of this great Heat Treat podcast that you put together.
Thank you so much.
That I can bring on all of this great technology and inner minds that I have over these years, and let's go.
So, Ron, how long have you been designing furnaces for?
Designing furnaces?
Yeah.
Well, I started in Holcroft. Actually, when Holcroft Loftus was just changing its name to Holcroft to the Holcroft Company in 1988.
Okay, so basically my age. So you've been designing furnaces for 35 years around.
Somewhere there, yeah.
Right, so you know a couple of things, a couple of secrets, and I have worked with you on many projects. So for the audience, I'm super excited about this podcast. Ron is gonna tell us and explain us on a very basic way, furnace design 101, because this guy is super smart. I have seen him designing on mechanical, combustion, electrical, a lot of things. And this podcast will be about, for the guys that are commercial heat treaters or captive heat treaters or suppliers, how do we design a furnace from scratch? What is the process? What do we have to take in considerations? Because, you know, it's very difficult to have one furnace design itself. Maybe it can be similar, right? But there are many variables that we have to take in consideration. So, Ron, thank you so much for doing this. Super excited. But before we start the technical conversation, just would like to have a little background of how you started on this business, the positions you went through. You are right now manager of projects and engineering for AFC Holcroft, but I believe you started as an engineer. And if you could just recap a little bit for the audience, your background and your development through the furnace industry.
Yeah, of course. So, you know, growing up on a farm, you get to use your hands and make things work. You know, you see and feel the steel on the tractors and the equipment. And from there, engineering was always a part of my mind. And so after the US Navy, I went to college and got my 4-year degree in mechanical engineering. That helped me understand a little bit, only a little bit. And when I was hired into Holcroft right out of college, I pretty much said, you know what, I don't want to design the furnaces that you build here without first knowing how they work. And so I spent 45 years out in the field service department, starting up furnaces in the different locations globally that we sent them. From there, then I went into the mechanical engineering group and I started designing the furnaces. Most of these things are custom. There's a very small percentage of what even up today that we design that are standard out of the box, just process the papers. These are custom pieces of equipment, so they all have different aspects that you need to keep in consideration when you're designing. So after a few years of that and going to other different types of thermal process environments, not just steel, but also incineration of hazardous wastes. And I moved into the electrical engineering group for a short time where there was a need. So I did some cross-functional training there to understand how do PLCs control furnaces, how do hardwire logic work, where do you determine to put a relay versus a PLC. Back in the days before safety PLCs were really a vogue thing now. So then some combustion understanding, and then, you know, found my way into management in helping the groups all work together to develop and design what the customer's needs are. And now I've been doing that for, I don't know, maybe 10 or 15 years now. And it's fantastic because every single day I come into work, it's something new. It's something different. You learn on every different project coming in, how to tackle a problem and solve it and make a customer happy with a piece of equipment that they ordered.
And that's I believe the training that you went through in your career is, I will say, will be like the optimal training for any guy related to heat treat, right? Because if you go on the field to do installations, I don't know, retrofits, maybe upgrades, you learn about how the furnace works, the applications. You see where's it gonna be, the heat treat. You learn material flow, and then when you catch the general functionality of the machine, then you went and understood and learned electrical engineering, PLCs, power, motors, comms, and then you actually it's like you're seeing the guts of a furnace, and then you go combustion, mechanical. So I believe that's like the best way to start learning, because you have to understand the application in order to design the machine which is going to perform the application. Would that be a true statement?
It's totally true, because an engineer or even a learning engineer may not quite understand that heat from these furnaces is not like a light switch you turn on and off.
Yeah, heat melts things, heat makes difficult to work around the area. Heat makes electronics melt away or malfunction.
Yeah, and if you just turn off the power, that doesn't mean that all of a sudden, just as quickly, all the heat is gone.
Also, heat makes the mechanics to expand and need to have a fine adjustments at when we have temperature.
Oh, of course. Yeah, all those aspects of the different materials and how they expand and grow. All of those can be put into a textbook, but when you go into practicality and you look at it, you have to be able to look ahead and see where are those things going to influence the materials that I put into the furnace. And it's not just thermal either. It's about the attack that happens from the environment in the furnace.
Mm-hmm.
We learned over the years that at a certain temperature range, high nickel alloys will start to rot away in this temperature range. So, selecting the right material with the right cost means a lot in the end to a customer.
So let's start and discuss how a furnace is designed and engineered, right? As you mentioned previously, mostly all furnaces, not to say all furnaces, are custom. There might be some standard, but everybody wants their own thing, right? So when let's say I'm the customer, what information will you need to have from myself in order to design a furnace? And if you just could add to the answer, what are the most common mistakes that you see when the customer delivers the information? What do they not take in consideration that it's an ABC need for you in order to start designing a furnace?
Right. Good question. So customers come to us with various different types of input, okay, for us to take and produce a design that will meet their need. Okay. Some will just say, we have this part here, I'll show it to you. We want to heat treat this part. We know that we want it to be this much hardness in the end, or we want to be able to use this furnace to stress relieve, or whatever the situation. They've got a product, they need a solution to make that product work. So in the early stages, the applications and the sales group need to ask the right questions in order to deliver to engineering a proper lineup, a scope of what that supply is. And now many different customers have their own standards and expectations, okay? You got the higher end tier ones, tier twos that say, here are the specifications of the equipment that we want you to design and deliver to us, versus the other customer that may be a small commercial heat treater trying to build up a company that say, I just need a furnace. I will rely on your company to provide us with the right equipment to do the job. So what input is needed? certainly you need to know what's the throughput expectation. How many pounds per hour? How many parts per hour or parts per load? We need to know what utilities they have. And if not, then we need to talk to them about utilities that they will need in order to meet the needs.
Well, what are the main utilities on a furnace?
The major utilities,
The main it's yeah, sure.
Electrical, compressed air, natural gas, or some other combustible gas. If it's going to be an atmosphere type furnace where you need combustible flames, or the combustibles on the inside to do the process needs. If it's an atmosphere furnace, you need to have nitrogen if it's an atmosphere type furnace to purge out and be safe. You could need an endo generator to produce the gases if it's an atmosphere furnace. You may need to have acetylene if it's not an atmosphere furnace, if it's a vacuum type process for that hardenability. You may need to have methanol if it's not an endothermic operation. So those are the types of, and ammonia. You know, certainly there's a lot more nowadays that are requiring carbon nitriding or any other process that they want to have nitrogen ammonia to do their job. So those are the big ones.
What about floor space? Is it always an issue?
Floor space, you know, it always seems that there's not enough floor space given to heat treat. It's always compact, and put these pieces of equipment into the smallest possible footprint as possible. And Carlos, is not only the footprint, but it's how to get the equipment that's built to that piece of footprint in the building. So that means we need the right size door. That means we need the right aisleway. So all of those are pieces of information that are needed by the design team in order to deliver an operating piece of equipment.
Also, just would like to add myself to your comment that when you get floor space, we have to remember that these things need to be constantly maintained, and they take a bunch of space as well to maintain. If you're taking tubes out from a furnace, or maybe a retort, or you want to take away a door or something, that's going to require a bunch of space to maneuver. And I believe that floor space is not well taken in consideration when designing a new layout at the plant. Wouldn't you agree with that?
I'll totally agree. Those are identification points that have to be made. The roof truss, you know, you can't just be able to put the equipment in the roof truss height limits. You also have to be able to install the equipment, so there has to be some room. You also have to maintain if there's something that needs to come out the top, you know, so it's not just sideways, it's also up on top. So all those need to be considered, or else there's discussions that need to be made too late.
Okay, so now we have all the information. You say throughput, you know the harness. You will ask for those things, the specifications, if they want their furnace painted blue or yellow, you name it, right? Which type of wire, if it's NFPA standards or CE. Okay, now you have all that. Yep. Then how do you kick off a furnace project design? And you know, if you could go through the different phases, while just I'm assuming you do a kickoff meeting with your team. You know, how do you address that to start designing manufacturing? And of course, I just would like to add, right now that the supply chain it's going into a hard time, how do you choose the right components? Because everybody wants their furnace on a rush.
Well, it has changed over the decades. It used to be that programs would be put in place long ahead of the need for the furnace to give suppliers time to put all this together and then deliver it on a timeline expected. That has changed dramatically over the years. And how we manage that is you need to have a project manager dedicated to make sure that all the different groups that are involved are well going down the same path. So that project manager kicks off the project to the mechanical group, which first starts. and then to the piping and combustion group, and then ultimately the electrical controls group. But all intertwined in that is the purchasing department who is told, I've got to buy these components. I need them on this timeline in order to meet the deadline at the end of delivery. So then of course, after it's designed, then it's all into the manufacturing to play their role to build. So the project manager is key to making sure that each of the engineering disciplines are well tuned in and have several cross-functional, we call cross-functional. That means we get the mechanical group talking to the electrical group and the piping combustion talking to the electrical group, everybody collaborating together so that we don't miss some large component or some large aspect of the order when it's too late. So project management schedules are all key to making a successful job.
And what are the most common challenges that you find during these processes?
Well, there's several different challenges. There's making sure that the timeline is realistic, making sure that the selected components by the engineer are purchasable. Okay, and when I say that, sure, anything can be bought, but is it so special that we're not going to get it in time in order to build and release and meet the customer? So the challenges are to make sure that there's communication from the engineer to purchasing. So there's also the missteps of one person's idea of how to design something versus what the company's standards are. Okay, if there's standards within a company that's designing equipment, that standard works, and don't reinvent it if it works. Let that standard move down the chain, because when engineering releases a standard component element to manufacturing knows what they're looking at. They don't have to figure out, how am I going to make this? It's odd. Purchasing is going to know, oh, I've seen this before. I can buy that from so-and-so. So standards are important. And if we misstep and all of a sudden start to over-engineer something just because a particular engineer wants to do that, then we fall into the pitfalls of timing and expense.
And let's take for an instance the combustion aspect, because we're talking furnaces and we're talking heat, right? So this is like our bread and butter, right? So in order to design a combustion system that can actually meet the requirements of heat treat, which will be described as ramping up, maintaining the temperature sometime, and then moving the load to a certain other area, how do you design, or how do you calculate a combustion system able to heat up a certain mass at a certain time at a certain rate and be able to run different parts with different variables? Just to pick one of the, we're talking furnaces, that's why I'm choosing combustion, right? But so I believe this will be very valuable to the audience.
Sure. Well, in general, like an old timer used to tell me, you know what? It's just a box of bricks with some heat in it. Okay. So if you take it to that level, it's a box of bricks with some heat in it. What heat do you need in order to heat up the product that's inside over a period of time that you want to, and actually get it up to the temperature you need to? So what input do you need? You need to know what's the material you're heating, because copper material is going to heat different than aluminum, different than metal, steels. You don't have to take it down to the true level of how shiny is the part coming in, because that does have an impact too. But it's also at what temperature you're going to be heating it up to. Are we talking about heating in a radiation type of environment, or is this at a lower sub-radiation level where predominantly it's convection heating? Okay, so those are the two big animals that we work with here. And so what do you need to know? you need to know how much heat is coming outside of the box. All right, so you're putting heat in, you're going to have some amount of losses that are going through the walls. All right, and you're going to have some losses that are going to the gases that you're pushing in that are exiting out. Okay, then you're going to have the product itself. So you take all of those together and you say, here's how much heat that I need in kW or BTUs, whatever the units you're going to use. That's how much we need. But then comes the other key, and that is where to locate the heat. If it's a box furnace, okay, it's in the whole box. Okay, but if it's a pusher furnace, now it's at what zones do you put what amount of heat? All right. If it's a roller hearth furnace, at where along the path do I need to make sure I have the right amount of heat to do the job? Some of it's heating, some of it's holding. All right, so you heat the product up, it's all at equilibrium. What do you have that you're losing that you need to continue putting heat in? It's the walls, it's the floor, it's the roof. Those areas that you lose the heat. So you got to be able to keep an amount of heat left over to control that product to uniformity, which is a total another animal. Okay, so you got enough heat, but to put it in the right spot so that your product is uniform. Okay, so you need to make sure that your design produces the uniformity in the product so that at the end, product that was on this side of the load equals the same as the product on that side of the load. So strategic location of heat, how it's transmitted, radiation or convection, and then, hey, after that, it's all about the quench.
It's all about the quench, good. And so, like your old timer told you, and I believe I know who told you this, but you know, it's a box with brick. How much heat you want to put in it, right? But you have to make sure that there's uniformity on that heat. That's when things start to get a little more complex. When we started to use recirculators, and I love how you mentioned it, strategically places where we hit the loads. So pretty much, but then after we have this box with bricks with heat, uniform heat, we need to move heavy loads continuously inside the furnace at industrial volume, right? So we have to implement mechanics, right? I believe you know, many people know mechanics, but they don't know mechanics when we're using high heat, right? Because everything distorts, or you know, it's not well aligned, or it starts to wear off. What do we need to have or take in consideration when dealing with mechanics inside a furnace?
Minimize the amount of mechanics you put in the furnace.
Minimize the amount of mechanics you put in a furnace. The less mechanics there's in a furnace, right? The better the result is going to be.
Use the simple rule of KISS. Keep it simple,
right,
Sammy. So you want to keep things simple, and that's why in the early years, decades in my earlier career, and even up to now, pusher furnaces were very reliable. They pushed large stacks of product through the length of a furnace repeatedly all the time. And that's because all the mechanisms were outside of the heat and only in the heat in a very short period of time when you use them. So if you put mechanics inside of the heat, you have to deal with how well is that going to be reliable over a life cycle. Because keep in mind that when you're dealing with moving parts, okay, what's the go-to material that you're going to use? Everybody knows it's a 330 or a 300 series, maybe a 600 series alloy. Well, I'll tell you, whether it's a casting or a wrought material, they will grow and they will shrink back, but they will grow again. Every time you cycle the temperature inside that furnace with that alloy, they don't grow back to the same original. And that's what we call creep and permanent growth, okay? So if you're putting together a nice little mechanic watch inside of a furnace and expect it to last over repeated heat cycles, you're prone for failure. It's not going to work. So the goal is minimize the mechanics that are in the furnace. Come up with a solution that you only use that mechanics when you need it, and then get it out of the heat.
Now we talked about combustion, we talked about mechanics. And right now, all the automation and electrical is like the high-tech stuff, we're coming to right now a PLC is like everything has a PLC, everything's electronic. Even if it's a motor, they have electronic boards. Nothing is only mechanical anymore. All mechanics now are wired to an electronic board or, well, I don't know, a computer, right?
Yeah.
So if you're saying that mechanics, to use as little as possible mechanics inside a forest, which I totally agree, right? But all the mechanics will have to be connected to an electrical device, a computer, a PLC, a controller, variable speed drive, if you wanna name it, right? How do we make sure these mechanics are aligned with electrical, right? And as well, how do we want to design this? I mean, is because electronics and automation is complex. We cannot say use the least automation you need, right? I mean, we have to keep it simple, use the KISS rule as well. But when we deal with automation, sometimes it's very hard to keep it simple.
Well, seriously, a lot of customers nowadays require data collection of some sort. And data collection results in the need for a computer. Okay, so we start at that level, and then we say, okay, they don't like to just have push buttons. They want to have or a light board that shows them what's on, what's off, what's moving, what's not. They want to see a touch screen, computer screen that they can go ahead and manipulate the furnace operation. So what controls that? A PLC, programmable logic controller. They were just coming out with PLCs, and those PLCs were huge parts of the cabinet. Sure, they took away a lot of the hardwire logic that was in there. Hardwire logic is, control relays that made things function. But now PLCs are very small, they're compact, they're little. But then you take it up to the next level of PLC to be a safety PLC. Now you can start to put combustion safeties into that PLC, minimizing even more of the control relays that are in that panel. So all of this is input to the PLC from, hey, is my device turning? So I've got a proximity switch on it, that's feedback. I've got a disconnect, is it open or closed? That's feedback in. And then you've got output. Output is motors, valves, solenoid valves for controlling atmospheres. You've got some of the controllers are built into these PLCs, or some of these controllers that are maintaining the proper temperature are what we call discrete instruments. Okay, they hang on the door of the cabinet separate from everything. So all of this is for the most part must-haves in this day and age. There's very few customers, but there still are, that will say, I don't want anything fancy. I want just to operate my furnace. Oh, but by the way, I want to minimize how many steps I need to take in order to make it run. Well, when you minimize steps that the user has to do, you need these logical controllers. You need these different pieces that are a part of the electrical cabinet and the controls.
And what's your opinion? And this is pretty common to everybody that uses computers or electronics. And you talked about the 80s, and there was the exponential growth of electronics and comms, computers, and everybody right now is talking about the quantum computers, etc. Right? But computers become obsolete faster and faster right now. Components switch software or hardware, or they just stop doing those, right? And furnaces are designed to have a lifetime of 50 years well maintained, right? How do commercial heat treaters or captive heat treaters can face this challenge when they bought a furnace, let's say 15 years ago, and they well maintain it, but their controllers and instrumentation is becoming obsolete.
Well, obsolete could be in the fashion of the computer itself.
Let's take for an instance Windows XP that was
So take Windows XP Professional, okay?
yeah, which was super reliable, and I know that I believe, you know, just for the record, I believe Windows XP is the best software Microsoft ever has developed. It run forever, but you know that now it's obsolete.
It's obsolete. It's obsolete in the fact that it's not supported. Windows 7 is out because they won't support it if there's a problem. Okay. Windows 10 is now, as of January of 2020, I believe it was, is the software that Microsoft will support. That's not to say that if a program is running on an older PC on a furnace, that it's not gonna, that all of a sudden it's gonna shut down. Okay, it's gonna work, and it's gonna work until its life cycle is over.
Yes.
So when it finally says I'm dead, I can't reboot my computer anymore, then ordering a new computer and putting that software on it may take a small upgrade in the software for it to communicate and talk, but it's not going to put their furnace out for weeks and months. Okay, so to remove the fear factor of, yeah, I see that these are quick cycle obsolescence, doesn't really mean that you're expecting your return on investment of your furnace to be the same.
Right.
Okay. Just like any other component that's on a furnace. Okay. Barber Coleman carbon controllers. Okay. Marathon Monitor carbon controllers years ago were the thing, and now you can't find them. I don't think you can even find them on eBay, but there are replacements for it to keep your furnace running. And I think that a lot of heat treaters need to put the computer system in that same package. There's value, extreme value when it comes to putting computers on furnaces, and it's not just to make a motor start and a motor stop, or a door to open, door to close. Softwares are put into these computers for better understanding of quality control, insistent on some suppliers to have that data for control validation, and all the other possible inputs that can come in for predictive maintenance, maintenance tracking, equipment talks. And so you want to have something that will listen to it.
Okay. Right now, like the main talk on the furnace industry is precisely what you just mentioned, that the furnace is a box with brake, with combustion, and then we talk about mechanics and things and electronics that those things have developed over 20, 30 years, right? But we have seen a substantial technology increase in the world, not on furnaces, on everything else, right? We're talking about big data, artificial intelligence, so smartphones, cloud computing, right? Where those things can actually do a match with what we're doing, right? What are the new trends? What are we gonna see? How the furnace of the future are gonna look? What's your opinion? I mean, are they gonna have, you know, everything now has Bluetooth. Our furnace is gonna have Bluetooth, right? It's very, the Moore's law is that this type of technology is becoming very simple. Everything's being linked to your phone. Why not a furnace?
Oh, for sure. For sure. And we have to move production facilities away from the secrecy, the secret sauce that they have in their operations, in order to allow for them to be comfortable with wireless type products, so that it can gain traction within their plant. We are seeing more and more wireless transfer cars, for example, to keep cables from running around in the roofs. But these are things that have to come from, we can sell them, but plants need to become comfortable with security. They have to become comfortable with who's going to get the password to come in and shut my furnace down. Okay. So that's one aspect. But when you mention what are we going to see going forward beyond just the technology side, okay, it's what are we going to see moving forward in the world of a customer coming to a manufacturer of furnaces to deliver. And those things, you know, if you take it back to the 60s when we had large amounts of long production rows of pusher furnaces, okay? You'll see a pusher furnace once in a while, but not as much as they were back in the 60s, 70s, 80s. But then it moved into the 90s where batch furnaces became big. And we sold the fact that they're very flexible and they can be sized to different shapes to meet whatever the production needs are. But then still that's ferrous metal, okay? So then you go into the 2000s and vacuum furnaces became big, sold very well against atmosphere type furnaces, right? And where those are coming to become obsolete in their own right because the persons in charge of buying those pieces of equipment that are very maintenance intense have gone, and now other people are there to pick up the pieces, have a choice to make, you know, what they want to buy. But what we see moving forward is lighter materials, okay, more aluminum, lighter materials, ADI, ductile iron has the strength. Look in the automotive world, which in some instances drives heat treat, but it's not really the full heat treat for us. They're looking for electric vehicles. Okay, so what's the heat treat in an electric vehicle? All right, they're faster motors, so they spin faster. And if you spin faster, you need to be more precise in the gear sets that you have. So I would say that my listening ear tells me that salt will make a re-resurrection from its past in the 70s, 80s. So that's what I see moving forward. Keep an eye on things that are electric vehicle related because it's coming. And regardless of people saying, you know what, we're never going to be able to do that, should beware because Europe in itself is mandated very green. Not like the US, but it will come. It usually does. So that's what we have to watch out for. Look out for more electric heated furnaces, less gas heated furnaces, okay, because of emissions.
So there's also a couple of processes, and I don't want to go to process because with electric car also comes FNC and night riding as well for those type of gears. But I will agree with you. I don't know if you watched the podcast with the heat treat doctor, but you know, I asked him how do he envisions to be the furnace of the future, and he said, well, a lot of electronics, you know, computer data and computers is driving everything. Low emissions, it has to go green, and it has to be automatic because as well there's a very big challenge with labor, and I believe the more automated a furnace line is, the easier it's going to be for the company. Do you have an opinion on fully automated lines?
Oh, I share that view. You know, the workforce, you know, there's always got to be a diverse workforce. Those that love to be on a factory floor and push steel through furnaces. But it's migrating away and into the more laborious the work like how do I make these furnaces? How do I design them? Or you know, I don't want to get dirty. So you know, automated systems, we've been doing more and more of them. We'll see how far that goes. Europe is very into automated systems. very few that they will actually put in place without them being automated, to the level of what we call a lights out scenario. Okay, we've sold several that are in Europe that are lights out, and that means on a Friday they're going to load up and queue up all the loads they're going to run, and then everybody goes home, and I do mean everybody goes home, and on Monday morning they come in and all of the product is finished, completed, and on the other set of tables to be offloaded. So that level hasn't really come into the US so much because probably insurance, but that happens and it's going to continue to grow.
Thank you so much, Ron, for sharing this vision of the future with us. Love talking to you, and thanks so much for sharing your knowledge, because you're a very knowledgeable person on this field specifically. And I do agree on you on everything you say regarding where's the future going. Of course, we need to take in consideration regulations like emissions. I don't want to say unions, but as well, unions don't like automation much. So things like that. So we have to take economies of scale and macroeconomies of countries as well in order to design a furnace. Countries also dictate how their furnaces want to be built, right? Because of politics and laws, I guess. But it's been great talking about technical stuff with you, Ron. But as well, you are a manager, a director. You manage a bunch of people. You're a great leader in your company. You have a bunch of responsibility. Now let's talk about the human aspect and the real challenges. I believe furnace design is easier, but managing people is a little more complex, right? So how do we manage engineers? I mean, because there's a bunch of very smart guys out there with knowledge, but they might not be good communicators, or they might do their thing their way, because there are many ways to get to a result. But how do you manage all those minds when you have a project in common, and for them to understand what they have to do, but to give them the flexibility to design a furnace or to find a solution to a problem in their own way that might not be what you envision, but it works?
Well, first, thanks for all of the things that you said about me.
It's true. I mean, otherwise you wouldn't be on the podcast.
But management and leadership. What I've learned is you have to be a good coach, and if you have a hammer as your method of driving, it won't be received very well. And so what you need to do is not do it yourself. You need to coach, and be willing to be patient enough to watch the young engineers or the new engineers learn and absorb the differences of how to design a furnace system from scratch, or even from a modification to an existing unit. So patience, coaching, having routine discussions. Don't leave them out on a limb and then bring them back after they've made a mistake and say what has happened here. It's make sure that you are approachable. Make sure that the coach and the player are able to work together to come to a common goal. That's really how I developed in my career here. I always have the philosophy that I don't know everything, and that I need to go to others that I can rely on for advice. If I can rely on their expertise and their years, that's where I'm moved into, and allow the younger ones to approach me and ask me, hey, how do I get past this? What do you think? And my first question will always be, well, first, what do you think?
It's been great talking to you, Ron. Now, for the last question, and what will be an advice for the new generation of engineers? And I'm not just saying just furnace engineers. What do you being an engineer in your life, and going through many different projects, different type of challenges, mistakes, great wins. What will be a nice advice that you could give to the new generation of engineers that you will have somebody to tell you when you started working for Hallcroft back then?
Patience. One of the hardest things for young engineers that I see now is patience. Have patience. Don't think that you're going to jump from a entry-level engineer to the lead engineer on the company and then to management in a matter of 2 to 3 years, maybe not even 5 to 10. Patience. That's number one. Number two is be humble. This industry that we have here is it's not rocket science, okay, but it's full of a lot of pitfalls. And as much as you may think that you know as a young engineer that you are terrific at your job, you will come upon a mistake that you do. And it's how you are able to humbly handle that mistake that you made and be able to learn from it and move forward in a good, positive attitude. Also, love your job. If you don't love your job, don't come to work just because you have to. Find a job that you love to do, where your passion is. Because when you have passion for the job that you're doing, you're going to love to come to work and you're going to show it and you're going to produce an outcome that you feel is yours. And it will be very rewarding in many respects, not just for you as an engineer, but also to those that you're delivering it to.
Thank you so much, Ron. You heard from Ron Waligora, manager of projects on AFC Hallcroft, 35 years of experience on the furnace field, designing furnaces. Thanks so much, Ron. It's been a blast talking to you, sharing experiences. And it's always great to also to have somebody to think that likes to share coach kits, right? And I do agree 100% with you with that the new guys, they don't have patience. They want to escalate really quickly because right now the world is in a rush. People don't have the patience to get things, right? So thanks so much, Ron. It's been a blast. I just would like to remind the audience that we're uploading weekly podcasts with power players of the heater industry like Ron Waligora. We're on LinkedIn, YouTube, Spotify, and don't miss next week's podcast as well. Please subscribe to the channel and give us a like. Thanks so much, Ron.